In this video, we're going to be doing source transformation with a dependent source. It's not something you normally want to do, but it's more to show you that it is possible and kind of the things to be careful about. So when I say source transformation, you're probably looking over here at this 30 volt and this 3 ohm and saying, oh, I can do a source transformation here, put this 3 ohm in parallel with this 8 ohm and combine them, and then do it again and then combine that resistor with the 6 ohm, and you'll get this thing all simplified down. Now that won't work, and I want to show you why. So let's pretend we did that. So just note that this is not the right thing to do. So say we, so this would be 30 over 3, and you'd be all happy because you got 10 amps, and then you would get your 3 ohm here, and you would have your 8 ohm resistor here, and you'd have your 6 ohm and your dependent voltage source. So now, the reason this doesn't work is because we no longer have Vx defined. I can no longer find Vx, so I don't know what the voltage here is anymore. And you're going to say, well, it's just the voltage across this 3 ohm resistor. And that is incorrect. Vx is defined between this node. We'll call this node, how about call this node 1? We'll call this node 2. We'll call this node 3. And we'll call this node 0. Kind of standard stuff. When let's work our way backwards. So this is node 3. This is node 2. This is still node 0. Where did node 1 go? If you notice, this is all now node 2. Node 1 disappears when I do source transformation. Vx is defined as the voltage between node 1 and node 2. So without a node 1, I can no longer measure Vx. It does not carry over with this 3 ohm resistor. That would be incorrect. So that's why you have to be a little bit careful. That's the major mistake someone would make here, is they would try to move this 3 ohm down. But in doing so, you condense this circuit and you lose your node here between these two, so you can no longer measure Vx. So don't do that. Instead, we want to look over here on the back side, and we want to do our transformation over here. So let's go ahead and draw the front side. So this is 30 volts. Here is our 3 ohm plus Vx minus. Here is our 8 ohms. And then what I'm going to do is, if I do a source transformation over here, I can move this 6 ohms in parallel with this 8. So that's what's going to happen. So 6 ohms. And just like with an independent source, this dependent source will turn into the other form. So instead of being a voltage source, this will be a current source. And so this will still be 2Vx, but it needs to be 2Vx divided by 6. Same stuff you did, the same exact math. So we take our voltage and divide it by resistance. Basically, V equals IR, and I equals V over R. So because this is now a current, I need to take my voltage, 2Vx, and divide it by my resistance, which was 6. And then I can combine these two. They will turn into, so 1 over 8 plus 1 over 6, 1 over R equivalent. So we have a common denominator of 24 here. So I would need 3 over here, and I would need 4 over here. You can also just use 48 if you don't want to figure out what it is. Which will be 7 over 24 equals 1 over R equivalent. I know it's not very pretty. R equivalent is 24 over 7. And if you really wanted to, you could put it into a fraction. It's approximately 3.43 if you wanted the approximate decimal point of that. But I would keep it as 24 over 7. So let's redraw that circuit. So we have 30 volts. We have our 3. We have our Vx. we have our 24 over 7. We have our current source. 2Vx over 6. You could call this 1Vx over 3 if you really wanted to. And really the last thing we can do, again, I can't get rid of this node 1 or this node 2. If I ever do that, then I can no longer measure this circuit. I can no longer measure the dependent variable, which is Vx. But I can do a source transformation and turn this back into a voltage source and put this in series with that, which may be of some use. So we'll do that real quick. And we're going to get 24 over 7. And then this will turn into a voltage source. Our polarity will match that. Let's clean that up so you can see a little bit better. And so this will now be 2Vx over 6 times 24 over 7. And if you simplify that, you will get 8 over 7 Vx. And at this point, that's all we can really do. But we can now find Vx with a single voltage loop, which is kind of the advantage. So again, we can't really do the full, and again, to be careful, node 1, node 2, I would not call this 3. You probably want to call it node 4 because it's not the same as the node we had up here. This is not the same node anymore. This is a different node. You still have your node 0 down here though. So I'd probably call this node 4 just to indicate that it's not the same node as this anymore. You're tempted to combine this 3 and this 24 over 7 together, but if you do that, your node 2 will go away and you'll no longer be able to measure Vx. So that is really the biggest challenge with when you have a dependent source, is you have to make sure you do not lose the nodes or the resistor, depending on what it is. If it's a current, then that current will generally be through a resistor, and so you have to keep track of where that resistor is. If it's a voltage, you have to make sure you keep your nodes. So in this case, this is as simple as we can go. So we would just do a KVL, probably just around this thing like this. We'll just call it around 1. So minus 30 plus Vx plus 24 over 7 I1, because this would be I1 here. No, you can't see any of that. Sorry about that. And then plus 8 over 7 Vx equal to 0. You'd have two variables in here. You have a Vx and an I1. You'd need another equation. Again, anytime you see a dependent source with a dependent variable, that dependent variable you can relate back through Ohm's law. So it's the 3 ohm resistor. So Vx will just be equal to 3 I1. And we would just say that I1 is equal to Vx over 3. We would combine these together and just do a little algebra. At this point, we've done all of the circuits, and we're just doing algebra. So 30 plus Vx plus 24 over 7 times Vx over 3 plus 8 over 7 Vx equals 0. And when you simplify that, 9.13 volts. So your Vx is all combined, you end up with 23 over 7 Vx equal to 30, and then you just do your algebra. So again, this doesn't make it a whole lot cleaner. It's just more to demonstrate that you can do source transformation with a dependent source. A lot of times you're not really going to want to, but it is possible. Again, with this voltage, the key here is the voltage is defined between nodes 1 and 2. I can't do anything that would cause node 1 or node 2 to go away. And if it was a current instead, then I'd have to make sure that wherever that current is defined, probably through a resistor, that resistor never gets combined with another resistor, because otherwise I won't be able to measure it. Again, there's special cases if it was in series with something, you could do that because the current wouldn't change. But being careful that our dependent source remains intact. So our dependent variable remains intact so that we can always calculate the voltage or the current through our dependent source. All right.